All right, let's get into it. We're about to dive into the huge world of computer science. And I'm telling you, it's so much bigger and more amazing than you probably think.
So, when you hear computer science, what's the first thing that pops into your head? For most people, it's coding, right? Tapping away at a keyboard, writing endless lines of code. And look, that's definitely a part of it. But it's kind of like saying architecture is just about laying bricks. The truth is, coding is just one city. Yeah, it's a major capital city, for sure, but it's still just one spot on this massive, interconnected continent of ideas. So today, we're going to pull out the full map. We're exploring everything from the absolute deepest foundations all the way up to the highest peaks of AI. Okay, so before we can even think about building a circuit or writing a single line of code, we need the blueprints. And in computer science, these blueprints, well, they aren't drawn on paper. They're forged from pure, uncut logic and mathematics. And this is maybe the most important thing to get right from the start. Computation isn't just something we made up. It's a process that's governed by these universal mathematical laws. Rules that were true long before the first computer was ever even plugged in. This is ground zero. And it all kicks off with this incredibly simple but powerful idea. Any statement can be boiled down to one of two things. It's either true or it's false. That's it. This binary concept, this on or off, yes or no, it is literally the fundamental atom of the entire digital universe. So fields like these, they give us the language we need. You've got sets and relations that help us group things together. Graph theory helps us understand how they're all connected. And then Boolean algebra gives us the rules to actually work with all of it. This is the language that's going to bring our machines to life. So great, we've got our abstract blueprints, this really cool language of logic. But how do you take something you can't even touch and turn it into a physical machine? A machine that can actually do the math? And this is where the magic happens. Seriously, this is the core trick of computer engineering. We take a purely logical thought, like A and B have to be true. We write it down with math, and then we build a tiny little physical switch, a logic gate, that actually enforces that rule using electricity. It's how thought literally becomes silicon. And then we just scale it up, way up. We take millions, now billions, of these super simple logic gates, and we start combining them into more complex parts. They become the most basic memory cells, things called flip-flops. Those get grouped into registers that hold numbers. And eventually, you build the whole shebang, the central processing unit, the CPU, the brain of the whole operation. What's really fascinating is that even down here, at the deepest hardware level, there are totally different philosophies. You've got RISC processors, which are kind of like having a simple vocabulary, but being able to speak incredibly fast. And then you have CISC processors, which have a much richer vocabulary, but take a little more time to form each word. Two different ways to think in silicon. All right, so we've built this incredibly powerful machine. But there's a huge problem. It only understands one thing: electricity on or electricity off. That's it. So how do we as humans actually talk to this thing?
The solution is pretty genius, actually. We build layers of translation. We call this abstraction. We don't try to speak directly to the billions of switches inside the processor. That would be insane. Instead, we build these bridges, and each layer gets us a little bit closer to a language we can actually understand.
And a key player here is the compiler. Think of it as a master translator. It takes the code we write in a language we can read, like C++ or Python, and it painstakingly converts the entire thing into the raw ones and zeros that the CPU can actually work with. And get this, there's more than one way to do it. A compiler is like translating a whole book from start to finish before you even start reading it. But an interpreter? That's more like having a live translator whispering in your ear, doing it line by line as you go. Both have their pros and cons. Now, the final and maybe most important layer of communication is the operating system. It's the conductor of the whole orchestra, right? It's managing the hardware, it's running all our translated programs, and it's making sure everything, from your mouse clicks to your monitor, plays together in perfect harmony. Okay, this is where it gets really fun. We've got a physical machine, we've got a way to talk to it. Now, with all that foundation in place, we can finally start building the incredible digital world that we all use every single day. Think about it. So much of our modern world just runs on data.
And SQL, well, that's the universal language we use to ask questions of all that data. It's how you find your profile on social media, how you check your bank balance. It's the language of information itself.
But here's the thing. In this world, it's not enough to just solve a problem. You have to solve it efficiently. And we actually measure this using something called Big O notation. It basically tells you how slow your program will get as you give it more data. Like finding something in a sorted list, super fast, logarithmic. But comparing every single item to every other item, that's quadratic, and it gets impossibly slow really, really fast.
We also build completely different systems depending on the job at hand. You have OLTP systems, which are built for speed. They handle millions of tiny little transactions, like withdrawing cash from an ATM. And then you have OLAP systems, which are built for deep thinking. They're for analyzing mountains of data to find hidden patterns and trends.
And of course, we have to connect everything together. That's where networking comes in. It also uses a layered model, just like we saw before. Each layer has a very specific job to do, from the physical wires all the way up to the app itself. It's what makes sure your email or your video stream gets packaged up, addressed correctly, and delivered reliably anywhere in the world. And that brings us to the final frontier on our map. This is where we take all of those layers we just talked about, the logic, the hardware, the software, the networks, and we try to build something truly mind-blowing. A world that can learn, that can reason, and maybe, just maybe, can even think. You know, when we talk about AI today, we're mostly talking about machine learning. And there are two main flavors. You can teach a machine by giving it tons of labeled examples. That's called supervised learning. Or you can just dump a sea of data on it and ask it to find interesting patterns on its own. That's unsupervised learning. But how will we ever know if we've actually done it? If we've created a true AI? Well, the classic test for this came from the father of computer science himself, Alan Turing. And the test is beautifully simple. If a human judge can't tell for sure if they're talking to a machine or another person, then the machine passes. And so this whole journey, think about it, from a simple true or false statement, all the way through silicon chips and compilers and global networks, right to the very edge of creating an artificial consciousness. That is the real, breathtaking map of computer science. And it leaves us with one heck of a question to think about, doesn't it?